The Tuas Finger One reclamation project is located at Tuas View Extension and is the first of the new Tuas Megaport's 4 fingers. 164.5 hectares of land, equivalent to 230 football fields, or about 1/3 the size of Sentosa Island, was reclaimed for Tuas Finger One. The 4-kilometer coastline was designed to berth large container ships in deep waters and massive caisson structures, each the size of a 10-story HDB block, were used to create the vertical wall. The additional reclaimed land, or ARL in short, is 31.5 hectares and was reclaimed south of the Tuas Finger One reclamation site to serve as a caisson casting yard. This location allowed the temporary casting yards to serve as a shared production base for 3 major reclamation projects, namely Tuas Finger One, Tuas Port, Phases 1 and 2 reclamation projects. This shared resource strategy ensured optimal use of land, reduced environmental footprint, and eliminated the need to build separate facilities, which reaped huge cost savings for the whole of government. Using sand rehandled from DSBA1, the ARL was reclaimed in stages. Shore protection rocks surrounding the sandbarrow area were first removed prior to the sand extraction. Both land and marine equipment were mobilized for the rocks removal. The removed rocks were then transported to a rock stockpile area for sorting and reused as shore protection for Finger One reclamation works. Land formation at ARL. After the rocks removal, a cutter suction dredger was used to mine the sand from DSBA1. A cutter suction dredger is a hydraulic dredger, a rotating cutter head to loosen seabed materials, which was then sucked up by a dredge pump and discharged at the ARL through a floating pipeline. The deposited sand was spread by bulldozers and backhoes to level the sand on reclaimed areas continuously. After ARL was reclaimed, thousands of piles were installed for the caisson casting yard and gantry tower foundation to support the weight of caissons during production. Steel double gantry towers, measuring 50 meters in height, 49 meters in width, and 70 meters in length, were erected to accommodate the slipform system and provide shelter for the 2 production lines. Upon completion of the caisson casting yard, a continuous round-the-clock operation was implemented to fabricate caissons daily. The caissons were orderly constructed over 4 major steps. In Step 1, a special hydraulic equipment called individual pushing caisson carrier vehicle (IPCCVs) was deployed to concurrently lift and transfer the caissons to each step of the production line inside the caisson casting yard. Each IPCCVs can support a maximum of 200 tons. This step serves as a maintenance area for the IPCCVs, but more importantly, it allows one set of IPCCVs to serve both production lines, achieving efficiency and cost savings for the project. In Step 2, the construction of caisson base slabs was executed. For durability of structure and control of hydration, Portland blast furnace cement with 70% ground granulated blast furnace slag was applied to each base slab. An automated curing system was adopted for curing. This technology, developed in Korea and patented in both Korea and Singapore, maintained the temperature difference between the internal and external concrete within 20 degrees Celsius to control unnecessary thermal cracks. After curing, the base slab was lifted 5 to 7 centimeters during its move to the gantry tower in Step 3. In Step 3, the slipform system was utilized for the production of caisson walls. An average of 6 days was required to produce and complete 1 unit of caisson in Step 3. During slipform operations, 72 hydraulic jacking units carrying a maximum jacking force of 40 tons each supported the slipform. The slipform truss consisted of an upper deck, a working deck, and a hanging deck. On the upper deck, rebar and concrete were supplied to the working deck. On the working deck, the fabrication of the caisson walls was carried out. The caisson was then transferred to Step 4 after the slipform works were completed. In Step 4, silane was applied to the upper portion of the caisson for durability enhancement. After all repairs were completed, the caisson was then transferred onto a floating dock and delivered to Finger One reclamation site via MPA-approved caisson sailing route. A total of 91 caissons were fabricated and transferred to Tuas Finger One wharf line for installation. Reclamation works at Tuas Finger One, soil investigation and survey works. Before any construction began on site, detailed soil investigation and hydrographic surveys were carried out along the proposed caisson alignment to understand the soil properties and seabed conditions. The data collected was used to assess the soil strength, identify weak layers, and determine the design thickness of the foundation layers needed to support the massive weight of each caisson. Dredging of Sand Key Trench. Based on the geotechnical findings, the first step in caisson foundation preparation was the construction of the sand key. Designed to satisfy caisson's overall stability and stringent settlement requirements for future port usage, soft seabed material was removed to expose the hard seabed stratum to form the sand key trench. Dredging was carried out using grab dredgers and cutter suction dredgers. Hopper barges and flat-top barges were utilized to transport the excess dredged materials to Finger One and the nearby Jurong Island Westward Extension Project site for reuse as reclamation materials. This initiative leveraged on the concurrent timelines of both projects, minimizing unnecessary rehandling works, thereby enhancing overall construction efficiency. Sand key filling and marine vibrocompaction. Sand was dredged from approved sand borrow areas and transported to site using hoppers or dredgers. It was then filled into the dredged trench and compacted using marine vibrocompaction method to strengthen the foundation to ensure stability and to prevent excessive settlement of the caisson over time. Rock mound works. After completion of the sand key, a graded rock mound was constructed on top. This layer acts as the final foundation for the caisson placement, designed to distribute loads, provide required lateral resistance, and accommodate the seabed irregularities. The rock mound was built using Class B rocks of approximately 300 mm as the core layer and 20 to 100 mm size rocks as the leveling layer. Each layer was carefully placed and compacted. A backhoe mounted on the rock mound work barge would transfer the rocks from the barge and discharged on top of the sand key through a movable fall pipe. The work barge utilized differential, GPS, and gyro compass to ensure precise placement. The barge also has a grading frame for initial leveling of the discharged rock. After discharging and compaction by tamping equipment, a gravel layer was placed on the rock mound, and special equipment mounted on a self-elevating platform was used to grade the discharged rock to the final level. Special attention was paid to the top level of the rock mound to ensure a flat level surface for ease and accurate caisson installation later on. Caisson installation. With the rock mound completed, the foundation was ready to receive the 91 prefabricated caissons, marking the next phase of construction, which was the installation and alignment of caissons at sea. After the caisson was loaded onto the floating dock, the caisson was transported to Finger One reclamation site approximately 6 kilometers and took 3 hours via the approved sailing route. Upon arrival, the floating dock was ballasted so that it was partially submerged for the caisson to float. Each unit, weighing thousands of tons, was maneuvered into position using tugboats and GPS. At the final installation location, each caisson was carefully lowered onto the leveled rock mound using a controlled ballasting process using water pumps. Caisson was shifted and aligned into the exact intended position using tugboats and GPS. Survey teams then verified the alignment and level of each unit to ensure precise positioning along the entire 4-kilometer stretch. Rock filter and geotextile. The installation process was primarily carried out using a long-reach crane barge equipped with a clamshell bucket. The crane barge first placed a layer of Class C rocks, 20 to 100 millimeters, followed by the installation of Class D rocks, 2 to 20 millimeters. Surveys were conducted after each layer of rocks installed to ensure accuracy and compliance with design specifications. For the geotextile installation, launching frame was carefully lifted, positioned, and lowered into the designated area to ensure proper installation. Scour protection. Scour protection was installed at the toe of the caisson to minimize erosion caused by currents, waves, and propeller wash. First, geotextile was laid, followed by the secondary rock layer using a grab crane. Lastly, bigger primary armor rocks were placed on top of it. Caisson preloading works. Concrete blocks were used to preload the caisson to improve bearing capacity and reduce future settlement. Trailer trucks and barges were used to transport the blocks to the preloading area. Installation of preloading blocks was followed by surcharge filling by excavator assisted by articulated truck to fill to the required height. Construction of caisson joint. Upon completion of the preloading works, adjacent caissons were structurally joined after cleaning using airlifting. Prefabricated rebar cages with welded spacer bars were installed into the gaps using a crane. Concrete was applied to create a continuous, retaining wall, forming the first visible boundary of the reclaimed land. Construction of box culvert. Box culverts at Finger One were constructed before the L-beam. There were 8 box culvert drain structures constructed along the caisson line. After caisson preloading works were completed, excavation of sand infill for the affected caisson cells was carried out until the soffit of the culvert bottom slab. Lean concrete was placed after compaction works was completed. The affected caisson cell walls were hacked to expose the embedded couplers, and the exposed concrete was roughened for better bond. Construction of L-beam. The L-shaped beam structure was constructed on top of caissons along the berthing edge of Finger One reclamation. It is a structural element that retains the soil backfill and where the future bollards and fenders would be installed. The formwork for the base of the L-beam was installed between the caisson corbels, followed by installation of rebars for both the base and wall. Subsequently, the base slab was casted. After it had set, formwork for the wall was installed and casted. The concrete was continuously vibrated during casting to ensure uniform concrete flow, proper bonding with the reinforcements, and elimination of voids to ensure that the required design strength was achieved. Construction of the northern slope revetment. A short stretch of approximately 200 meters length of slope revetment was constructed at the northern edge of Finger One. Sand key foundation was constructed, followed by compacted sand fill, which formed the bund. After completing sand trimming and conducting a joint survey to verify the slope and levels, the geotextile material was carefully laid over the slope in preparation for the shore protection installation. Secondary and primary rocks were the shore protection placed over the geotextile by a grab crane at the seaside and excavators at the land side. At the upper part of the revetment, the rocks were hand-pitched to form a leveled surface. Reclamation filling and fill material. With the caisson wall installed, reclamation filling began behind the caissons in carefully sequenced stages, using a combination of dredged marine clay, good earth, and sand, transforming the vast body of water to a stable, buildable land. Sand filling and sources. Sand required for the project was mined locally at DSBA-2 and imported from various countries like Cambodia, Vietnam, Myanmar, Philippines, and United Arab Emirates. For imported sand, bulk carriers transported the sand to Singapore. The sand was then break bulk and transported to the reclamation site after volumetric survey and sampling to verify the sand quantity and quality were conducted. Cranes on board the bulk carriers, assisted by excavators, transferred the sand from the cargo holds to small pelican barges moored alongside the bulk carrier. These barges transported and discharged the sand via conveyor belt system at the Finger One reclamation area. For locally sourced sand, various types of dredgers, such as cutter suction dredger, grab dredger, bucket ladder dredger were used, and the sand was transported to the reclamation site by conveyor barges. A trailing suction hopper dredger was also deployed to mine sand from deeper areas of DSBA-2 and transported to be discharged at Finger One area. Sand filling behind caisson and vibro compaction. Sand was filled up to 60 meters away from the caisson face to enhance stability and provide good drainage to prevent water pressure buildup behind the caissons. Sand was pumped through a pipeline from the trailing suction hopper dredger for filling behind caissons. Subsequently, the sand was compacted by deep vibro-compaction method. The vibrator was lowered into the ground, assisted by water jets at the bottom. Upon reaching the designated depth, the bottom jets were closed, and flushing continued through jets positioned near the top of the vibrator. The vibrator remains at the depth until either the predetermined amperage was achieved or the preset time elapsed, whichever occurred first. Once the target criteria were met, the vibrator was raised to the next compaction level, typically at intervals of 0.50 meters to 0.75 meters, and the process would be repeated until the vibrator reached the ground surface, ensuring effective sand compaction. Alternative fill materials: good earth and dredged material. As sand is relatively expensive, it is designed for used in critical areas, and alternative fill materials such as good earth and dredged materials were explored to be reused at non-critical areas of the reclamation works. The dredged material from Sand Key was used as fill material for the reclamation. Cutter suction dredger, trailer hopper dredger, and grab dredger were used for dredging of Sand Key. The dredged soils were then loaded onto hopper barge and transported to the reclamation site for direct filling. The reuse of dredged material promotes sustainability and supports a circular economy. Good earth was delivered from approved land-based construction sources and dumped at Finger One. The approved good earth materials were filled in layers from the existing seabed level to plus 4 meters CD. Land machinery, such as bulldozers and excavators, were mobilized to spread and level the delivered good earth fill material. Temporary drainage diversion. While preparing for the reclamation works, temporary drainage diversion of the existing drain and outfalls was ongoing, which was crucial to redirect water flow and maintain drainage flow during the reclamation works. Soil improvement works, prefabricated vertical drains, and surcharging works. In order to accelerate consolidation of the soft soils for the newly reclaimed land, prefabricated vertical drains, PVD, combined with surcharge loading was used. This process would reduce residual settlement under the future operational loads. Prefabricated vertical drain, PVD installation starts by attaching an anchor plate to the end of the PVD, then retracting into the hollow mandrel of the installation rig. The mandrel was hydraulically pushed into the ground to the required depth. The mandrel was withdrawn, leaving the PVD in place. The PVD rig was moved to the next position, and the process was repeated until all PVDs were installed. Subsequently, surcharge was placed on top of the reclaimed land. Articulated trucks and backhoes were used for transporting and placing of surcharged sand. Soil instrumentation monitoring results would provide an indication of the consolidation progress and determine the period of surcharging required. Upon verification that the settlement requirements were met, the surcharged sand was removed by excavators and shifted by articulated trucks to the next phase to be surcharged. Post-soil investigation was also carried out to verify that the soil improvement works requirements were met. Surface compaction. Following removal of surcharge fill, the surface was leveled by bulldozer. For areas where the top 2 meters up to final platform level of plus 6 meters CD were filled with sand, it would be compacted by the vibrating tamping method, followed by roller compaction. When top 2 meters were filled using good earth material instead, it would be compacted in layers using vibratory roller compactors. In situ field density tests were carried out to ensure compaction has achieved the acceptance criteria. Completion of works. With the completion of soil improvement work to prepare the land for future development, this marks the completion of the reclamation of Tuas Finger One. Satellite images captured the project's transformation over the 8 years. Every 6 months, the coastline evolved as more caissons were installed and new land took shape behind them. Driven by methodical, precise, careful, and safe engineering control, the Tuas Finger One reclamation project successfully reclaimed 164 hectares of land with 4 kilometers of waterfront length in multiple phases. Each phase was handed over progressively from 2015. allowing downstream infrastructure works to begin without waiting for full completion. Upon its completion, the newly reclaimed land will be used for industrial purposes and redeveloped subsequently for port use.